Okay, thank you for introducing this at the beginning. So it's the beginning. It's the middle of June 10th for me. I know it's probably the end of the day for some of you, but this day has been set aside by the scientific community to think about systemic racism in our institutions, with a particular focus on our Black colleagues. So I wanted to share two articles specific to the geosciences. The first by Robin Bell and Lisa White, that was published last month in Scientific American. And this one highlights the critical need for diversity in the geosciences, specifically to address climate change, because we know that climate change is not felt by all communities in the same way. And the second is by Kahaley Dutt. It was published in Nature Geoscience, December of last year. And if there was any confusion about representation in the geosciences, this article points out that under 4% of tenured faculty or tenured track positions are held by people of color. At the end of the presentation, I can share these in the chat, but I just ask, even if you're not a scientist, please read these two articles today. So now to bring it back to the Gulf Stream trajectory. On Monday, we heard from Jeremy Jackson about Earth system science, in which he mentioned water's high heat capacity and the role of the oceans in regulating global climate by transporting heat around the planet. And the Atlantic meridional overturning circulation is shown here in the schematic as part of that heat transport. Meridional just means north to south, if that hadn't been made clear. Here, the red arrows show warm surface currents and blue arrows show deeper, colder currents. This is relevant to the Gulf Stream trajectory because the Gulf Stream is part of the system where warm water flows along the east coast of North America. An example of how this is relevant to us today, part of the Gulf Stream heads towards Northern Europe and keeps that Northern European climate relatively mild. If you think about the latitude of Scandinavia, for example, or the UK, it should be very, very cold, but the delivery of that warm water keeps the climate relatively mild. The strength of the AMOC through time is shown below in red, and you can see that it's variable. And in fact, throughout periods of Earth's history, we know that it has gotten significantly weaker. There is evidence to suggest that this is weakening today, and the consequences of that weakening would be widespread cooling in the Northern Hemisphere, a decrease in precipitation, and strengthening of storms across the North Atlantic. So this is a flow in the vertical with warm water at the surface and colder water at depth. And this schematic shows a really helpful perspective. So we can follow the Gulf Stream. I'm not sure if you can see my cursor, but we can follow the Gulf Stream where it starts in the south, where the surface of the ocean is warmed by the sun, and evaporation makes the surface waters mostly salty. And as it journeys north, it cools. And I mentioned part of it goes towards Northern Europe, but another part of it cools and sinks near Greenland and Canada, forming North Atlantic deep water. And it returns south as a cold current. So one literal trajectory of Gulf Stream waters brings us down to the seafloor. The cross-section also shows the vertical exaggeration of seafloor topography and highlights the vast scale of this ocean circulation. So given the scale, systematic measurements are kind of our only way to begin to understand this type of ocean circulation. It's not really something that you can perceive with your five senses. This cartoon also shows the location of the rapid array, a collection of sensors that measure velocity, temperature, and salinity in the water column. We also heard about these on Monday. So since this Tavola is organized around sort of a theme of perception, it's useful to point out the sort of scientific way of perceiving. First, I want to, I guess, notice the size of the instruments that that I mentioned as part of this rapid array are about as big as people, but the way that we use that information is just a different, not a physical way of understanding. So we can perceive the ocean through our observational platforms, but the first step of data analysis, more often than not, forces people to engage with the data delivery system that looks like this middle screenshot, and data that end up looking like basically a bunch of numbers. And I just kind of want to say that, like, I'm, theoretically, like, trained to do this and understand these data, but even when I see like lists of file names and things like that, it's hard to engage with information this way. And I think that we can do better by remembering our own physicality and try to bring the relevant perspective back into our analysis and understanding. So on a more personal level, I have some interest in overcoming some of the challenges of data and interpretation, and worked a little bit on the problem of interpreting 3D structures within the ice sheets. These structures can also not be sensed through our bodies because they are buried beneath the ice, and they have to be measured with a radar. So like the rapid array, our radar profiles show a slice through the ice, and we're left to interpret multiple 2D slices like this black and white image that you see on the left. However, using 3D visualization techniques, I've tried to properly orient these slices so that someone could move around them, like you see on the image on the right, rather than have to build structures in your mind's eye. And it's still the wrong scale, but it removes a barrier, maybe, I hope, removes a barrier to understanding by providing relevant physical orientation. So I sent my ocean fellow friends an experiment that would hopefully allow them to experience the relevant physics behind the thermohaline circulation and the Gulf Stream's vertical trajectory. Like I said before, the circulation, or maybe I didn't, I don't know, I hope I did, this circulation has to do with density, which is controlled in the ocean mainly by temperature and salinity. And so in these cross sections, you see what the ocean looks like in an elevation view, or a section view going through, with the temperature on the left and the salinity on the right. And what's most important to notice is how strongly layered the ocean is in temperature and salinity. And if you focus on temperature, you can see the cross-section is strongly stratified. Cold water is on the bottom and warm water is on the top. And it doesn't look like water masses are going to move vertically because dense water is already in its position at the bottom. However, you could imagine that if you put very cold water at the top of this, you could set off a circulation pattern like the one that we saw in this schematic of the AMOC. So this is the stratification that we can try to simulate to get an understanding of how water masses with different densities behave when they encounter each other. And this is the principle behind that density-driven circulation. So I'm going to show a video, hopefully this works well, that Barbara and Pietro made when they tried to experiment with the interaction of different water masses with different temperatures and salinities. Without instruments to measure, we're left to quantify the water properties with our own senses. I also want to point out this was also an attempt to get us all sort of out of Zoom and interacting with the physical world again.
Fancy. Still too warm. Right, now this water is very cold and it will go at the bottom. Pietro, this is the very warm, actually it's really hot, water, sweet, no salt, that will go on top of the salty water. Let's see how the experiment works. It looks like another big mass. Because to the eye, the line of separation is here. Yeah. So below is really dark. Above is really light. Yeah. I don't know if the machine reads it. I think it's like...
I'm going to stop it there, and to bring it back to perception, notice how the choice in color really mattered here. And if Barbara and Pietro weren't looking for it, they may not have seen the subtle line marking the difference between the two water masses. Oh dear, okay. So it was hard to distinguish because of the tracers and the colors shown. And this actually highlights the idea very well that color can be deceptive even in data visualization. And in fact, there is an oceanography paper dedicated to representing temperature and salinity in a way that is perceptually uniform and sort of allows a more true interpretation of the data. So in the left column, the same color scale is used for both temperature and salinity. And it's kind of confusing because the same color scale is used. You might think that both of them represent temperature and one of them is flipped. And of course, you can read this with the sort of annotations on the plot, but it doesn't jump out at you. It's not intuitive. You also might interpret there to be boundaries because of this bright yellow line here. Whereas if you look at the color scales on the right, you can see that the gradients are a lot smoother. There is absolutely no doubt in your mind that two different properties are being shown here. So just to sort of highlight that the choices we make in how we represent things really can change the way that we understand them. To bring it back to one more experiment, this is Jean's simulation, and I want to introduce it in terms of temperature and salinity space, which is the space that oceanographers think about. So she studied the interaction between hot fresh water and cold salty water. And on the right, you see a graph with salinity increasing along the x-axis from left to right and temperature increasing on the y-axis from bottom to top. And each of the curved lines is a line of constant density called an isopycnal. So the hypothesis was that cold salty water would be on the bottom. And she didn't include measurements here, but I tried to shade regions on this temperature and salinity plot to illustrate her water mass choices. So the blue water sits all the way on the bottom right, where salinity is high and temperature is low, and the opposite is true for the yellow. And you can tell by the constant density lines that they intersect that the blue one should be denser and should sink. And so let's see what her experiment looked like. And the cold salty water was introduced on the bottom, and in fact stayed on the bottom because it is too dense to float. Okay, so in the ocean, we can plot temperature and salinity of different water bodies in this temperature and salinity space and see where they fall. And so recall that the North Atlantic deep water formed as the Gulf Stream waters cool, and other deep water masses form in Antarctica, Antarctic bottom water and Antarctic intermediate water. And now that we understand this graph a little bit better, hopefully, we can note their relative positions and see what their respective densities are. And just by looking at this, you could guess that the Antarctic bottom water would sit on the bottom as it is the most dense, the Antarctic intermediate water would sit on the top, and the North Atlantic deep water would be somewhere in between. And so if you look at another view through the ocean, that's in fact what you see, the Antarctic bottom water on the bottom, the North Atlantic deep water, again, the vertical trajectory of the Gulf Stream in the middle, and the Antarctic bottom water sitting, Antarctic intermediate water sitting on the top. If anybody wants to try this experiment again with 3 water masses, I highly recommend it, although it can be quite challenging to avoid mixing. And I just want to end by saying thank you to all of the Ocean Fellows who participated in this. And I hope that this sort of helps us talk about ocean circulation in a way that is maybe a little bit more intuitive to us. Okay, thank you.